Dear students, today we will discuss pivoting. So why we need pivoting? Actually, Gaussian elimination method or Gauss-Jordan method does not guarantee the solution of system of linear equation in all the time, but sometimes it fails to give the solution of system of linear equation. So in that case, we need pivoting. So how we can define pivot element? A pivot element is an element at the position R okay, of a system of linear equation which can be used to eliminate unknown at the position R for rows R plus 1, R plus 2, so on R plus n is called pivot element, and the rth row is called pivotal row. So it means if the first element at the matrix or diagonal element is not equal to 0, we will see a non-zero element in the same column but below this diagonal element. Okay, so actually this non-zero diagonal element is called pivot element. Okay, what are the elementary transformation? Sometime we called elementary row operation. Elementary transformations include rows and column operations applied to linear system of equations, which yield an equivalent system. Elementary transformation may include following operations. Number one, interchange of rows or columns are possible. Number two, scalar multiplication of rows or column. And number three, replacement of rows or column. For example, a row can be replaced by the sum of that row and a multiple of any other row. So these three steps includes in elementary row operation or elementary transformation. So to interchange the rows or to swap the rows, elementary operations are performed. Next is the pivoting methods. It is observed that during Gaussian elimination, it is necessary to interchange rows of the augmented matrix whenever the diagonal element of the column currently being processed, known as the pivot element, is equal to 0. So when we need to perform the pivot method is that when the first diagonal element is 0. If the first diagonal element is non-zero, then we don't need to interchange or swap the rows. Moreover, multipliers of rows cause round-off errors in performing elementary transformation. Therefore, it is helpful if it can be ensured that the multipliers are small. This can be accomplished by performing row interchanges or pivoting, even when it is not absolutely necessary to do so for elimination to proceed. Okay, sometimes it is not necessary to perform row interchange, but if we apply these pivoting strategies or pivoting methods, so then we will get a solution in a more accurate form. The first pivoting strategy is called trivial pivoting. So in the trivial pivoting, for a square matrix A, if the diagonal entry is equal to 0, then we will locate the non-zero element in the same column but below this diagonal entry. So in the same way, for a square matrix A, if diagonal entry, that is APP, is equal to 0, then we will locate the first row below pth row in which the entry is not equal to 0, and we will swap row k with row p. This will result in the new element APP is not equal to 0, which will be called as the first diagonal entry. Okay. So in trivial pivoting, simply we will interchange the rows to avoid from the 0 element at the diagonal. Next is the partial pivoting. For a square matrix, A, if diagonal entry equal to 0, then we will locate row U below row P such that we will get the maximum entry in this column. So that is why we can write it AUP absolute is equal to maximum of AIP, while so I is equal to 1, 2, 3, so on n. So what's the difference between trivial pivoting and partial pivoting? In trivial pivoting, we can interchange the first row with any of the row below this first row. But in partial pivoting, we will locate the maximum entry in the same column where the this diagonal entry lies. So next is the scaled partial pivoting. In the scaled partial pivoting, at the start of the procedure, compute scale factor for each row of the matrix A as Si is equal to maximum of Aij for I is equal to 1, 2, 3, so on n. So it means in the similar column, in whole of the matrix, we have to find this maximum element, which we called with Si. So then the scale factor are interchanged with their corresponding row in the elimination steps. The scaled partial pivoting strategy is as follows. In a square matrix A, if APP is equal to 0, no is not equal to 0, no need to interchange rows. And if it is 0, locate row U below P in which AUP is an element actually below APP, and this element will be divided with SU, and SU is a scaling factor, which is the actually the maximum value in whole of the matrix. So then we will get the different entries, and the maximum of this entry will be as a scaling factor. So in this case, we will obtain a UP is not equal to 0. Now switch row U and P such that a PP is not equal to 0. This we will explain by giving some examples to understand how the scaling factor can be computed. Okay, next is the total pivoting. For a square matrix A, if APP is equal to 0, then locate row U below P and column V to the right of P in which AUP is equal to maximum of Ij and AUV is not equal to 0. Switch row U and P and switch column V and P so that new element APP is not equal to 0. Total pivoting is also called complete pivoting, full pivoting, or maximal pivoting. So it means in total pivoting, we can interchange rows and column as well. We can swap two rows or two column to find the maximum entry in whole of the matrix. And this entry we will bring at the first position, and which will act as a first diagonal entry. The example is that solve the following system of linear equations using Gaussian elimination method. Apply in trivial pivoting and partial pivoting. So this is the system of linear equation. We construct matrix A of coefficients, matrix X of variables, and matrix B of constants. So this can be written as the form of system of equation Ax is equal to B. Okay, we construct an augmented matrix by including constants in matrix of coefficients, and we perform elementary row operations just to transform this matrix into an upper triangular matrix. So look at the first position, this diagonal entry is 1. Okay, so here we don't need to interchange rows because the first entry is 1, and we can perform elementary transformation easily. So by subtracting from second row the multipliers of first row, I mean R2 minus 2R1, and with the third row we multiply first row with 5 and will subtract from the third row, and we will obtain this column. So now no need to perform any further operation on this first column, but we need to perform further operation by the second pivot element, which is -1, because this is the second diagonal entry. Okay, so then we perform the operation and we have reduced this entry 4 into 0 and -5 into 0. So now the operations on this second column are completed. Next, we will consider -2 as the third diagonal entry and the pivot element. Okay, and by performing operation, we have reduced 7 into 0. So this matrix is completely transformed into upper triangular matrix, and now we perform this backward substitution to get the solution. Minus, okay, this 1.5 x4 is equal to -3, and then we substitute this value in this equation and we get the solution 132 minus 2. The next example is that use Gaussian elimination method to solve system of equations. Apply trivial pivoting, partial pivoting, scaled partial pivoting, and total or full pivoting. Again, the system of equation can be written as Ex is equal to B, and the augmented matrix is constructed as follows. So now observe that the first diagonal entry is also non-zero. So that is why we don't need to swap rows. Okay. So we have transformed this first column as required 1 0 0 0, and next the next diagonal entry is the 2. So that is why again this is non-zero element, and we don't need to swap rows or to uh, interchange columns. So we can consider 2 as a diagonal element and also as a pivot element. So perform the operations on the second column. So this will, we reduce this 9 and this 5 into 0. So this operation on the second column is completed. And next, the third diagonal entry is -5 by 2. Okay, so we perform the operation. This -5 by 2 is again non-zero. So we perform the operation with the -5 by 2, and this -7 by 2 will be reduced to 0. So just observe that this matrix is reduced as a upper triangular matrix, and it is easy to find the solution. -5x4 is equal to this one. So x4 is equal to -5.6. 2x3 is equal to this one. x2 is equal to x3. Okay. Next, partial pivoting strategy. To apply partial pivoting strategy, we proceed as follows. Okay. So look at the first column, 1 0 2 2. Okay. So in the first column, we will find the highest value. So highest value is 2 at position 3 1. Also in the position this 3 1 and 4 1. So locate largest element in first column, which is a31 is equal to 2. Interchange first row with third row. It gives 2 0 1 2. Okay. Now perform Gaussian elimination by using a11 as a pivot element. So we reduce this first column as desired. Okay. So okay, next we will perform operations on this second column, and okay, apparently this 2 is the second diagonal entry, and is the pivot element. Locate largest element in the but in the partial uh, pivoting strategy, we always need to locate highest value in the column. Okay, so this column contain 2 9 by 2 minus 4 because we have to consider positive values, not negative. Okay, so just if we simplify 9 by 2, it is 4.5. Okay, so then which is A32 is equal to 9 by 2 is equal to 4.5. So this is the actually the highest value is 9 by 2. So this contains row third. So here we need to interchange second row with third row because this is the highest value. So here we have interchanged these rows. So now this minus 9 by 2 becomes the diagonal entry. And we performed operation with this. We have reduced this column as desired. So then we will come to the third column, and in the third column this minus 5 by 9 is the diagonal entry, and minus 9 19 by 9 is the next entry, but we will evaluate the which is the bigger one. So minus 19 over 9 is the bigger one, so that's why we will interchange this third row with the fourth row. Okay, and then minus 99 over 9 become the uh, pivot element, and we perform operation with this pivot element, and this column also reduced as we desired, and ultimately this matrix is transformed into upper triangular matrix. So then we obtain the results as a backward substitution method. So that is the difference between partial pivoting, okay, and scaled partial pivoting. So this is actually partial pivoting strategy are similar as a scaled partial pivoting strategy. Okay. So what's the difference between now trivial and partial pivoting? In the trivial pivoting, we just interchange rows, okay, if the element in the first row is a 0. In partial pivoting, we interchange the first element if it is 0 with any other non-zero element in the same column. In scaled partial pivoting, we calculate scaling factor to know in which row, with which row we have to interchange this first row. So that is the difference. And in total pivoting, we can interchange rows as well as columns. So that is the simple difference between these four methods. Again, I can repeat, in the trivial pivoting, we just have to interchange the first row with any other row if the first diagonal entry is 0. In partial pivoting, we have to interchange the first row if it contains this A, B, P equal to 0 with any other row which contain the largest value in the same column. And in scale partial pivoting, we must have to calculate scaling factor to know with which row we have to change. And in total pivoting, we can interchange rows as well as columns. Okay, so that is the difference. And what's the application or what's the advantage of this pivoting? It will ensure it will ensure the solution of elimination methods. For example, this Gaussian elimination method or Gauss-Jordan method. So uh, that is the lecture of the day. Okay, so we will see next time.